Look up at the night sky. Every star you see, every point of light scattered across the darkness is a sun. Many of them have planets. Some of those planets might have water, atmospheres, maybe even life. The universe is vast beyond comprehension, filled with worlds we will never walk on, wonders we will never witness, mysteries we will never solve, because we will never leave the solar system. Not in 100 years, not in 1,000, probably not ever. I know what you're thinking. That's pessimistic. That's defeatist. Humans have always overcome obstacles. We went from horses to airplanes in a single lifetime. We put men on the moon. We sent robots to Mars. Surely, eventually, we'll reach the stars. But the stars are not Mars. The stars are not the moon. The distances involved are so incomprehensibly vast, the energy requirements so astronomical, the timescale so immense, that interstellar travel isn't just an engineering challenge. It's a confrontation with the fundamental laws of physics, laws that don't bend, laws that don't break, laws that don't care about human ambition. I'm Leonard Susskind, and I've spent my career studying the deepest structures of reality. Quantum mechanics, relativity, string theory, the nature of space and time itself. And I can tell you that the physics of interstellar travel is not on our side. The universe has built a prison around every civilization, and the bars of that prison are made of light speed, thermodynamics, and the cold equations of energy and distance. Let me show you why. First, let's talk about distance. Because until you truly grasp the distances involved, you cannot understand why interstellar travel is so difficult. The nearest star to our sun is Proxima Centauri. It's about 4.24 light years away. That means light, traveling at 300,000 kilometers per second. The fastest anything can travel in this universe takes over 4 years to get there. 4 years doesn't sound too bad, right? We've had space missions that lasted longer. Voyager has been traveling for over 45 years. So what's the problem? The problem is speed. Voyager 1, the fastest object humanity has ever launched, is traveling at about 17 kilometers per second relative to the sun. At that speed, it would take Voyager over 73,000 years to reach Proxima Centauri. 73,000 years. Human civilization is only about 10,000 years old. We'd need to wait 7 times the length of recorded history for Voyager to reach the nearest star. And Proxima Centauri is our neighbor, the nearest star. Most stars in our galaxy are hundreds, thousands, tens of thousands of light years away. The galaxy itself is 100,000 light years across. At Voyager speeds, crossing the galaxy would take over 1 billion years. So clearly, we need to go faster. Much, much faster. And this is where the physics starts to hurt. To travel to another star in a human lifetime, you'd need to travel at a significant fraction of the speed of light. Let's say 10% of light speed. At that velocity, you could reach Proxima Centauri in about 43 years. Still a long time, but conceivable. A person could leave Earth as a young adult and arrive as an elderly explorer. Not ideal, but possible. But here's a question nobody wants to answer honestly. How do you accelerate a spacecraft to 10% of the speed of light? Let's do some physics. The kinetic energy of an object is 1/2 times mass times velocity squared. At 10% of light speed, that's 30,000 kilometers per second. For a modest spacecraft, let's say 1,000 tons, about the mass of the International Space Station, the kinetic energy would be approximately 450 million trillion joules. To put that in perspective, that's roughly equal to the total energy consumption of human civilization for an entire year. All the electricity, all the fuel, all the power generated by every power plant, every car, every factory on Earth for 12 months. That's how much energy you'd need to accelerate a single modest spacecraft to 10% of light speed. And that's just the kinetic energy. That's not counting the energy needed to produce the fuel, to overcome inefficiencies, to decelerate when you arrive. If you want to actually stop at your destination rather than zoom past at 30,000 kilometers per second, you need to double the energy. You need fuel to slow down as well as speed up. This is where the rocket equation becomes your enemy. The rocket equation is a simple consequence of Newton's laws. It tells you how much fuel you need to achieve a certain velocity change. And the answer is exponential. The faster you want to go, the exponentially more fuel you need. For chemical rockets, the kind we use today, the numbers are absurd. To accelerate to 10% of light speed using chemical propulsion, you would need a fuel mass so large that it's essentially infinite. The rocket would be almost entirely fuel with a payload so tiny as to be useless. Okay, So chemical rockets won't work. What about nuclear propulsion? Nuclear reactions release millions of times more energy per kilogram than chemical reactions. Surely nuclear rockets could do it? Nuclear propulsion helps. It helps a lot, but it doesn't solve the problem. Even with nuclear fission or fusion, the energy requirements are staggering. You'd need to carry enormous amounts of nuclear fuel. The spacecraft would still be mostly fuel. And you'd have all the problems of operating nuclear reactors in space for decades, radiation shielding for the crew, the risk of catastrophic failure, the challenge of building something that can function reliably for a half-century voyage. Let me give you some numbers. Project Daedalus was a study conducted by the British Interplanetary Society in the 1970s. They designed, on paper, an unmanned spacecraft that could reach Barnard's star about 6 light years away in 50 years. The spacecraft would use nuclear fusion, igniting pellets of deuterium and helium-3 to produce thrust. The result? A spacecraft weighing 54,000 tons at launch. 54,000 tons. The Saturn V rocket, the most powerful rocket ever built, could lift about 130 tons to low Earth orbit. You would need over 400 Saturn V launches just to get the fuel and components into orbit. And this was for an unmanned probe. No deceleration at the destination. It would fly past Barnard's star at 12% of light speed, take some pictures, and keep going forever. For a crewed mission with the ability to slow down and actually do something when you arrive, the numbers become even more impossible. But wait, you might say, what about antimatter? Antimatter is the ultimate fuel. When matter and antimatter annihilate, they convert 100% of their mass into energy. E equals ms squared with perfect efficiency. Nothing else comes close. And you're right. Antimatter is incredibly energy dense. A single gram of antimatter annihilating with a gram of matter releases about 180 trillion joules of energy. That's equivalent to about 43 kilotons of TNT. More than twice the energy of the Hiroshima bomb from 2 grams of material. So why don't we use antimatter? Because we can't make it. Not in any useful quantity. The total amount of antimatter ever produced by all the particle accelerators on Earth combined is about 20 nanograms. 20 billionths of a gram. And producing that tiny amount consumed vastly more energy than the antimatter contains. To fuel an interstellar mission, you'd need tons of antimatter. And even if we could somehow produce that much, we'd have to store it. Antimatter annihilates on contact with ordinary matter. Any container you put it in would be vaporized. You'd need magnetic containment, perfect magnetic bottles that could hold antimatter for decades without a single failure. One microscopic leak and your fuel tank explodes with the force of a nuclear weapon. Antimatter isn't a solution. It's a fantasy, a beautiful theoretical possibility that practical reality has rendered impossible. So what else is there? What about light sails? The idea is elegant. Instead of carrying fuel, use a giant sail and push the spacecraft with light. The light could come from the sun, or better yet, from a powerful laser array on Earth or in orbit. This actually works in principle. The Breakthrough Starshot project has proposed sending tiny gram-scale probes to Proxima Centauri using exactly this method. A massive laser array would accelerate the probes to 20% of light speed. At that velocity, they could reach Proxima Centauri in about 20 years. But notice the caveats. The probes would be tiny. Gram scale. A few grams of electronics, a camera, a transmitter. No life support. No people. No way to slow down. They would flash past the Proxima system at 60,000 kilometers per second, gathering data for a few hours, then continue into the void forever. And the laser array? It would need to be enormous. Gigawatts of power focused on a tiny sail tens of millions of kilometers away. The engineering challenges are immense. The cost would be in the hundreds of billions of dollars, and you'd get a flyby. A brief glimpse, not exploration, not settlement, just a postcard from another star. For actual human travel, light sails face the same fundamental problem. To accelerate a human-carrying spacecraft to any significant fraction of light speed, and then slow it down at the destination, you need either a laser array at both ends, which means someone has to get there first to build it, or you need to carry fuel for deceleration, which brings back all the mass ratio problems. The physics is relentless. Every solution creates new problems. Every workaround hits another wall. Let me talk about time. Because even if we could somehow achieve the speeds necessary for interstellar travel, time itself becomes the enemy. At 10% of light speed, the journey to Proxima Centauri takes 43 years. That's a significant fraction of a human lifetime. The crew that leaves Earth will be old when they arrive, if they survive the journey at all. Their families on Earth will be dead or elderly. The world they left behind will be unrecognizable. They will be strangers in both places, belonging nowhere. But 43 years is optimistic. Remember, you need to accelerate and decelerate. You can't just instantly jump to 10% light speed. The acceleration has to be gentle enough for humans to survive, probably no more than 1 or 2 Gs for extended periods. At 1 G of constant acceleration, it takes about 35 days just to reach 10% of light speed, and another 35 days to decelerate at the destination. That adds to the total journey time. And what happens during those decades? The spacecraft must function perfectly for over 40 years. Every system, every component must work reliably for longer than most machines on Earth last. Your car doesn't run for 40 years without major repairs. Your computer becomes obsolete in 5. But an interstellar spacecraft must work flawlessly for decades in the most hostile environment imaginable, with no possibility of repair, no resupply, no rescue if something goes wrong. The crew must survive in a tiny enclosed environment for 40 years. The psychological challenges alone are daunting. We struggle to keep astronauts mentally healthy on the International Space Station for a year. Imagine 4 decades in a metal can with the same handful of people, knowing that Earth is years away at the speed of light, knowing that if anything goes wrong, you will die alone in the void between stars. And then there's radiation. Outside the protective cocoon of Earth's magnetic field and atmosphere, space is filled with deadly radiation. Cosmic rays, high-energy particles from distant supernovae and black holes, sleeting through space at nearly the speed of light. On a journey of decades, the cumulative radiation dose would be enormous. Cancer risk would skyrocket. Neurological damage would accumulate. The crew might arrive as invalids, their bodies ravaged by radiation, unable to do the work they came to do. We could shield against some of this radiation, but shielding adds mass, and mass makes the propulsion problem worse. Every kilogram of shielding is a kilogram that needs to be accelerated to 10% of light speed. The more protection you add, the more fuel you need, the larger the spacecraft becomes, the more impossible the mission gets. Now let me address something that science fiction has taught you to believe in. Faster than light travel, warp drives, wormholes, hyperspace. The idea that we can somehow cheat physics, find a loophole, slip through the cosmic speed limit and travel between stars as easily as we travel between cities. I've spent my career studying the structure of space-time, and I can tell you that faster than light travel is almost certainly impossible, not just difficult, not just beyond our current technology. Impossible in a deep fundamental sense. The speed of light isn't just a speed limit. It's woven into the fabric of space-time itself. It's the conversion factor between space and time. It's the speed of causality, the maximum rate at which any influence can propagate through the universe. Violating the speed of light isn't like breaking the sound barrier. It's like dividing by 0. It doesn't compute. It creates paradoxes. It breaks physics. What about warp drives? The Alcubierre drive is a theoretical construct where space-time itself is distorted, contracted in front of the spacecraft and expanded behind it. The spacecraft doesn't move through space faster than light. Space itself moves, carrying the spacecraft along. It's a clever idea, but the mathematics requires exotic matter with negative energy density, matter that almost certainly doesn't exist. And even if it did, the energy requirements are absurd. Early calculations suggested you'd need more energy than exists in the observable universe. Later refinements reduced this, but the numbers are still impossibly large, and there are serious theoretical problems. Hawking radiation at the warp bubble boundary, the inability to steer or stop, the possibility that you'd destroy your destination with a burst of accumulated radiation when you arrived. Warp drives aren't engineering challenges. They're almost certainly physical impossibilities dressed up in mathematical language. What about wormholes? Wormholes are theoretical tunnels through space-time, shortcuts connecting distant points. If they exist, you could step through a wormhole in the solar system and emerge near Alpha Centauri, bypassing the vast distance between. But wormholes, if they exist at all, would require exotic matter to hold them open. The same impossible exotic matter that warp drives need. And traversable wormholes might be fundamentally impossible. Quantum effects might cause them to collapse the moment anything tries to pass through. The energy required to create one might be infinite. And even if you could create a stable wormhole, you couldn't use it to travel to somewhere you haven't already been. You can't create a wormhole to Alpha Centauri unless someone has already traveled there, at slower than light speed, to place the other end. Wormholes aren't a solution. They're a theoretical curiosity that probably can't exist in the form science fiction imagines. The universe has rules. Those rules are not negotiable. And those rules say that nothing travels faster than light. Nothing. Ever. No matter how clever you are, no matter how advanced your technology, no matter how much you want it to be otherwise, we are trapped. Trapped in a cosmic prison of our own making, surrounded by walls of light speed and vast distance. The stars are there, taunting us with their presence forever beyond our reach. Let me tell you what this means for humanity, because this isn't just an abstract physics problem. It has profound implications for our future, our place in the cosmos, our understanding of ourselves. We evolved on this planet. We are adapted to Earth, to its gravity, its atmosphere, its magnetic field, its temperature, its ecosystem. We are not suited for space. Space is hostile, deadly, utterly indifferent to human life. And the distances between stars are so vast that they might as well be infinite. The solar system is our home. It's the only home we will ever have. Yes, we might colonize Mars someday. We might build habitats on the moons of Jupiter and Saturn. We might mine asteroids and construct space stations, but we will never leave. We will never reach another star. We will never join a galactic community, if one exists, because we cannot cross the void between stars. This is the great filter, perhaps. The reason we see no evidence of alien civilizations. Maybe intelligence arises throughout the galaxy, but every civilization reaches the same conclusion we're reaching now. The stars are too far. The physics is too hard. They stay home, trapped in their own solar systems, unable to spread, unable to contact each other, alone in the cosmic silence. Or maybe we're wrong. Maybe there's physics we don't understand yet. Maybe some future generation will discover something that changes everything. I'm a physicist. I know that our understanding is incomplete. General relativity and quantum mechanics don't fit together. There might be deeper laws, stranger possibilities that we haven't glimpsed yet. But I wouldn't bet on it. The speed of light has been tested to extraordinary precision. It's been confirmed by every experiment ever conducted. It's embedded in the structure of space-time, in the equations of electromagnetism, in the foundations of quantum field theory. It's not a tentative hypothesis. It's one of the most solid facts in all of physics. And even if faster than light travel were possible, even if warp drives or wormholes could somehow work, the energy requirements would still be astronomical. The engineering challenges would still be immense. The universe doesn't give things away for free. Every solution to one problem creates new problems. Every shortcut has hidden costs. I've made peace with this. I've accepted that humanity will probably never reach the stars. Not because we're not clever enough, not because we don't dream big enough, but because the universe is what it is. Physics is not a suggestion. It's a constraint. And sometimes the constraints are absolute. But there's another way to look at this. The solar system is not small. It's vast beyond anything our ancestors could have imagined. From the sun to the outer reaches of the Oort cloud is perhaps 2 light years, trillions of kilometers, countless worlds, countless resources, countless mysteries to explore. We could live here for millions of years without exhausting what the solar system has to offer. We could build civilizations on dozens of moons. We could terraform Mars, perhaps Venus. We could construct habitats in the asteroid belt, mine the moons of Jupiter, extract helium-3 from the atmospheres of gas giants. The solar system is not a prison. It's a playground of unimaginable scale. Maybe that's enough. Maybe the stars were never meant to be ours. Maybe our destiny is here, in this one small corner of the galaxy, living out our existence in the warmth of a single star. And there's one more thing, one consolation that physics offers. We can't travel to the stars, but we can see them. We can study them. Light travels freely across the cosmos, carrying information from the farthest reaches of the universe. With our telescopes, we can observe galaxies billions of light years away. We can study the composition of exoplanet atmospheres. We can search for biosignatures, signs of life on worlds we will never visit. We may never walk on a planet orbiting another star. But we might, someday, know if life exists there. We might detect the chemical fingerprints of alien biospheres. We might even, if we're incredibly lucky, detect signals from intelligent civilizations. We could know that we're not alone, even if we can never meet our cosmic neighbors. That would be something. Not everything we dreamed of, but something. a small victory against the vast indifference of the cosmos. The stars are out of reach. The distances are too great. The physics is too hard. We will never leave the solar system, but we can still wonder. We can still explore what we can. We can still build something meaningful in this small corner of the universe that is and will always be our home. Look up at the night sky tonight. See those points of light, those distant suns, those unreachable worlds. They are beautiful, they are mysterious, and they are forever beyond our grasp. That's the truth. That's the physics. That's the universe we live in. And somehow, despite it all, we're still here, still looking up, still dreaming, still reaching for what we cannot have. Maybe that's the most human thing of all. Thank you for listening. The stars will never be ours. But the wonder of seeing them, of knowing they exist, of understanding why we cannot reach them, that is something no distance can take away.